Probability is built from the ground up on the language of sets. So that's where we begin. In this first video, we meet sets and their elements, the two special sets that anchor everything, the operations that combine sets, the idea of a partition, the algebraic laws, and finally the Cartesian product. Get comfortable here, because every idea in this course casts a set-theoretic shadow. A set is simply a collection of objects which we call its elements. Picture a box holding a handful of distinct objects. Each one is an element of the set. If an object X belongs to a set S, we write X is in S. If it does not belong, we write X is not in S. Two sets are equal exactly when they contain precisely the same elements. Equality of sets is equality of contents, nothing more. Now suppose every element of one set is also an element of another. Then the first is a subset of the second. This still allows the two sets to be equal. When they differ, we call it a proper subset. And here is a fact that will become useful. Two sets are equal if and only if each is a subset of the other. That double inclusion is how you prove two sets are the same. How do we actually specify a set? If it is small, we just list its elements inside braces. More often, we start from some collection and keep only the elements with a given property. Starting from the integers, the even numbers are all x in the integers, such that x is even. Read the braces as the set of and the bar as such that. Two special sets deserve names. The first is the empty set, the set with no elements at all. It may look useless, but it is the natural answer whenever a condition is never met. The second is the universal set, written capital omega, the collection of all objects of interest in the problem at hand. Once we fix omega, every set we care about lives inside it. Remember this symbol. In probability, omega has a special name, the sample space, the set of all possible outcomes of an experiment. With a universal set in hand, we can define the complement of a set S. First, here is S, a region inside omega. The complement of S is everything in omega that is not in S, all the rest of the frame. We write it S with a small c. As a sanity check, the complement of omega itself is the empty set. Outside of everything, there is nothing. Now we combine sets. Throughout, picture two overlapping circles, S on the left and T on the right, sitting inside omega. The union of S and T is everything that lies in S or in T or in both. We shade both circles completely. The union holds anything caught by either one. The intersection is stricter. Only the elements that lie in S and in T at the same time. That is the overlapping lens in the middle and nothing else. Sometimes two sets share no elements at all. Their intersection is the empty set. We call such sets disjoint, and we will lean on disjointness again and again, because for disjoint events, probabilities simply add. Finally, bring the circles back together. The difference S minus T is the set of elements that are in S but not in T. Take the left circle and carve away the overlap. What remains is S minus T. This is also called the complement of T relative to S. The same idea as before, measured inside S instead of inside all of omega. Here is a structure worth singling out. Take a set and break it into pieces so that no two pieces overlap, and together the pieces use up the whole set. A collection of non-empty, disjoint sets whose union is the whole thing is called a partition. Every point of the disk lands in exactly one wedge. No gaps, no double counting. Keep this picture in mind. When the sample space is partitioned into cases, the probability of any event can be assembled piece by piece from its overlap with each case. That is the law of total probability, and a partition is exactly what makes it work. Set operations obey an algebra, much like ordinary arithmetic. First, order matters, so we use parentheses to show precedence. These two combinations are generally different sets. When in doubt, parenthesize. Two combinations, though, always agree, the distributive laws. Intersection distributes over union, and union distributes over intersection, exactly mirroring how multiplication distributes over addition. The most useful identities are De Morgan's laws. They describe what happens when you take the complement of a combination. Here is the complement of the union of S and T, everything outside both circles. That very same region is the intersection of the complements. the points outside S and outside T. Complement flips union into intersection. And this is not limited to two sets. Take the complement of a union over any index set, finite or infinite, and you get the intersection of all the complements. De Morgan scales to as many sets as you like. There is one more way to build a new set, and it is the one that lets probability talk about several things at once. Start with an ordered pair, a first object and a second object, where the order matters. The Cartesian product of S and T, written S cross T, is the set of all ordered pairs whose first entry comes from S and whose second entry comes from T. Take S to be 1, 2, 3, and T to be A and B. Pair every element of S with every element of T, and you get a grid, here 6 ordered pairs in all. That grid is the Cartesian product. When we reach random vectors later in the course, this is the construction that lets us describe two quantities jointly. And that completes our tour of sets. We have the elements and subsets, the empty and universal sets, and the complement, the operations and partitions, the algebraic laws, and the Cartesian product, the alphabet that the rest of probability is spelled with. In the next video, we put this language to work and study functions, the special relations that send each input to exactly one output and the bridge from outcomes to numbers.